Hello, my wonderful students. We're going to take a look at a principle, a simple principle, that really will affect all your learning and computing. Doesn't matter what you're going into, coding, cybersecurity, networking, whatever. The importance of hardware is found in what it allows software to do. This is just, as I said, a fundamental principle. CPUs get faster, computers get faster, RAM gets faster, storage gets faster. All of it gets more capable. Why is it becoming more capable? Because we need to do more in software. Software is what pushes that. We need to be able to put this into software. We need better graphics for our games. We need more shading. We need AI. Well, that really is reliant on the hardware. Now, traditionally, the CPU handled everything. So we're going to take a look at a board right now and look at the components on that.
This motherboard received some damage from lightning. What is all this stuff? What are all these little parts doing? I mean, take a look at those little two chips right there. And what about that one? And that one? Now there's some bigger ones. We can make some assumptions about what that is and what that is. This one tells us what it is. It's audio. There's another little one. Man, what are these doing? Now, obviously, we can tell that's where the CPU goes. It's got a little lever. Now we can put the CPU and lock it down. It's got holes in the board where we can mount the heatsink and fan. And then, of course, we have the ports on the back, all the ways to connect to this system. As a matter of fact, I would assume, I am not sure, but I'd assume that one right there is probably for the networking. Either that or there's one down in here for networking. What do these chips do? Well, these chips have specific code inside of them, so they have software. We don't call it software, we call it firmware because we put it in there. It's burnt in, as they say, or it's coded onto those chips. The logic of what that chip is going to do. I would assume that those two have to do with bringing information in and out of these slots, which is RAM. These are bigger. I would assume one is the front side bus, meaning how to talk to the RAM and to the CPU and to the graphics card. That's what the front side bus does. In any case, every single electronic device we have has these little tiny chips in them that have logic programmed into them for what they are going to do. Here's slots that we can upgrade the system with. These are likely meant for graphics, but you can put something else in there. Right here is a little mount for a SSD, a solid state disk. There's another one right here, and it's got a heatsink on it. I've taken the heatsink off of that one so we can see underneath it. So let's use, for instance, one of the chips over here, maybe this one as an example, and say, okay, well, we've got right here a network adapter. And that network adapter is Ethernet. And it has to be encoded or programmed to take an electronic signal coming from this motherboard and convert it into an electronic signal that's acceptable to go out the network. And then, of course, to bring information in from that network adapter, change that information so that it's presentable to the computer system. And that is going to be programmed into one of these little chips to do that. That's its job. That's its sole purpose. It basically would be considered a processor, but only for processing Ethernet traffic. also known as a transceiver, to take digital code internally and make it acceptable for transmission externally, and vice versa. Lots of little processors programmed to do specific things. And yes, some of them are bigger because they're going to handle all the information about SATA and about what type of RAM should be put in here and how that type of RAM works and the type of CPU and how that works to assist the data communications across the system.
So you can see that, and there's all these little tiny specialized chips on there. There was a lot fewer of those chips back in the day. The CPU actually was the one that had to do the majority of the crunching. And over time, it was apparent that, hey, we can offload this. We can push this over to a specialized chip that's going to do that. And then the CPU can be freed up to do something else. And that helps speed up the system. Right here on this side of the screen, you see that's an Intel design. And this is looking at the system on a chip tile of that Intel processor. They've done some 3D stuff. You can see these different tiers that it's going off to. And over on this side is Apple's M4. And what happened with this, again, lots of times it's really pushed in the media. Media always has its own desire and their own ways of looking at things. A lot of, especially in the tech media, you have to understand that most of those writers in the tech media are not tech people. They're journalists that have an interest in tech. So in other words, if you said, look, you can't write about tech anymore, you got to do something else. Most of them would be fine with that. Only a few would say, well, I'm not going to write anymore because I'm so into tech. So they don't quite see things the same way as tech people themselves do. Basically, what happened here is Apple was using all of Intel's stuff for all of their PCs. And basically, they got to a point where Apple's like, well, we're getting a lot more power, computing power, using less power, but getting more computing power out of our mobile processors in the way that those are being designed. Intel, what are you going to do here? And I guess Intel didn't have a good enough plan because they share these plans. I mean, Intel's got plans for 10 years from now, what they're doing. So Apple left them and made their own silicone, their own central processing unit for their computers that's based on what they were doing on the phone. And these processors have become very powerful. So performance with less power consumption then matters as we are in this era where we really want batteries to perform the best that they can. Well, if you're going to suck all the power out of them, there's not a lot you can do. And Intel is making a lot of strides in that area, but the reason they're making those strides is because Apple basically said, see ya. And it's pushed Intel to go, oh, we really have to do something now because instead of just plugging our computer in the wall, people want to use it without a plug. And you can say, well, hasn't that always been there? You know, you've got notebook computers and hasn't always been there. Yeah, well, you can still plug it in the wall. And so their motive was a lot more, can we get through a plane flight? But we'll dumb down our CPU while you're on your plane flight. And then once you get off, you plug it in. That kind of thing, that kind of attitude. So really what you're seeing here is just some single core performance and some relative performance. So this is not total, but you'll see here at the top, there's Intel. There's an Intel Core i9 right there. And then there's the Apple M4 that's coming out. And how much faster that is than an i9. What you may not realize, because you may not be following CPUs, processors, is this is an extremely expensive chip, and this is an extremely expensive chip, and this is the low base chip. The M4 is what they would put into a Mac Mini or an iMac, something like that. That's just like, hey, there's your general processor. You want something more beefy, then you pay more, and you get. And this is the Max, right? That's their top tier one. Actually, I think their Ultra is above this. In any case, right, that's a huge performance boost. And we have the same thing here. Here's an Apple M3 Pro Snapdragon. As we come down, here's an M1 There's a Ryzen 7840U. There's a Core i7 that's a 1380. So that's a pretty new chip. And you can see the performance is much higher on these. Now, the reason I bring this out is because the better your CPU is at performing, and the better your computer, the whole design of the whole system with all those little chips on it, the faster that is, and that's what we mean by better, then the more capable it's going to be for whatever software wants to be written for it. And that's a very alluring to people that are writing software. If they can go, hey, I got this great idea, but it's really slow over here, I'm going to do it over here where it's not slow. I want people to see my software performing how it performs. Now, the other thing with this is from a security perspective. So let's take a look at this little diagram. This is cybersecurity layers, 7 layers of cybersecurity. The idea is when you're dealing with cybersecurity, and it doesn't matter if you're going into cybersecurity, everybody needs these principles. You've got different layers that you have to protect. The human layer, and that's where you're educating people and saying, hey, don't click on that email. Perimeter security, when you're dealing with the perimeter of your network and the perimeter of your physical location and keeping locked doors and so on. Then actual network security, where you're trying to keep your network safe. Endpoint refers to the notebook, the PC, the cell phone, whatever it happens to be. And then application security. And that has to do, did you code it correctly? Are you asking the right questions? Are you putting the right safeguards into your software? Data security. Well, software is often, these applications are often accessing data on some back end. Is that secure? Which, when you look at it, we're dealing with software, 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 software. Part of this is not, because you're dealing with the actual physical perimeter. And then, of course, you're not really dealing with software here. You're dealing with how the humans think. And this last one, really mission critical access, that is making sure that whatever you have here, whatever these things are in this mission critical assets, have even more security on them. So really, this is not different. It's just saying, hey, you're focusing on these things. You might have a mission critical network with mission critical PCs in it and mission critical applications with mission critical data, right? All rolled into that. The point is, all of it's software. Every single bit of it is software. When we look at something like this, you have to remember that there is code inside of here. How do we read and write this information? How do we move this from here to here? Why do we move it from here to here? And the same for all the chips you saw on the board. Somebody wrote software. Now, yeah, I'm using the term software to mean programming. Somebody programmed that. Somebody had to code it in using whatever language is needed for these chips. Same thing happens throughout these layers. Every single one of these layers, you have switches that have this software, except in all of those situations and all of those little chips and all of these network components and all of these computer systems, we don't term it software. We usually call it firmware. In other words, it's encoded into the chip. It's firm into the chip. Nonetheless, it's all programming. All of it is programming. All of it is coding. That means that you can have problems within that code that somebody can exploit at any one of these layers. This one, again, if you're talking about network perimeter security, every single one of them. That is important to understand. That concept is fundamental. And the reason why it's fundamental is as you go through these different courses, even if you're not going into cybersecurity, you're going to hit security within our client systems or our endpoint systems, and that is in CIS 190 and 191. And then you're going to deal with it in the A plus course, which is CIS 180, and you're going to deal with it in the networking course, which is CIS 195. And so it's important to understand why do we have to have all these different levels of security? Why do we do certain things for the PC to make sure it's secure? Why do we do certain things for our data system, make sure it's secure? Why do we do that? Because all of it somebody had to code, and they may not have been thinking about what another devious person might do to manipulate that situation to get data that they shouldn't be getting or get into something that they shouldn't be into. So remember that concept. It's all software, it's all firmware, and they may have weaknesses in that. So there has to be updates on your firewalls. There has to be updates on your wireless routers. Has to be updates on computer systems themselves. There has to be all these updates to try to make sure everything is secure from this point of view. All right, thanks for watching. That's just a short little video. Take the test if there is one available to you. And if you got any questions, let me know.